Ouais, aussi.
Je fais cette présentation en anglais.
Les termes, je fais l'intro français, la copie français, et le corps en anglais.
Tu vois, c'est bon, c'est filmé. Je vais réduire les fenêtres. Mais ça tourne tout. Voilà, ça tourne. Je te laisse.
Très bien. Je salue Clément Duhart, l'impétrant, qui va présenter son travail doctoral, soutenir sa thèse. Je salue mes collègues, membres du jury, et vous aussi, mesdames, messieurs. Mon nom est Francis Rousseau, et je serai, c'est ainsi qu'en a décidé le reste du jury, c'est un grand honneur pour moi, le président du jury et donc l'animateur de cette soutenance. Aussi Clément, et avec grand plaisir, je te donne la parole pour 45-50 minutes. On m'a dit que tu préférais 50, je montre que c'est un peu une pédale haute. Donnons la parole, nous allons t'écouter avec attention, pour que tu puisses présenter ton travail. À toi.
Merci. Donc, tout d'abord, merci à tous d'être présents pour ma soutenance de thèse qui s'intitule Vers une intelligence ambiante organique, EMA, qui est donc le nom de l'ensemble du framework qui a été développé au cours de ces 3 ans et demi de thèse. Donc, j'ai mené au sein du laboratoire du LITIS et du MIT Media Lab, pendant que j'occupais le poste d'enseignant-chercheur à l'ECE Paris. Donc, je vais tout d'abord vous apporter les éléments de base dans une introduction pour vous présenter l'informatique organique et l'Internet des objets, avant de vous présenter les 3 grands domaines, les 3 grandes contributions de cette thèse, avant de conclure. Dans l'introduction, on va parler d'Internet des objets, de qu'est-ce qu'on appelle l'informatique organique, ce qui va m'emmener aux motivations de cette thèse et à la fameuse question qu'est-ce que EMA, ou qui est EMA. Donc l'Internet des objets, ça peut être vu comme en fait l'extension de l'Internet au sein de nos habitats de vie. C'est-à-dire historiquement, le web pouvait être vu comme la construction d'une immense base de connaissances digitales, partagées, accessibles par tous. Et elle a suivi un certain nombre d'évolutions, avec notamment l'apparition des web services qui nous ont permis le développement du e-commerce, les réseaux sociaux, etc. Derrière se cachent les communications machine to machine, qui sont apparues avec ces technologies. Et depuis maintenant quelques années arrivent, on a tous entendu parler des objets connectés, et donc à terme l'Internet des objets, c'est-à-dire tous nos objets seront connectés les uns avec les autres. Et certains même vont vers un web 4.0, où en fait on aurait des systèmes intelligents qui géraient à la fois notre identité numérique sur la toile. Donc au lieu de faire nos requêtes sur Internet, sur Google, on pourrait imaginer un agent intelligent qui le fera en notre place, et inversement avoir des agents intelligents qui vont piloter nos espaces de vie. Donc c'est un peu dans cette dynamique d'évolution que s'inscrivent mes travaux. Et principalement l'Internet des objets, c'est avant tout une réunion de 3 challenges technologiques, qui sont tout d'abord la conception des objets eux-mêmes, donc faire de la microélectronique. Et à partir du moment où on ne peut pas décorréler ça avec les problématiques énergétiques, à partir du moment où on va commencer à avoir tous nos objets connectés, ça va bien sûr des ampoules, mais ça va notre grille-pain, etc. Il y a un moment où il va falloir que ces systèmes qui tournent en permanence consomment peu d'énergie. Et donc ça va avoir des conséquences fortes en fait, sur leur capacité de communiquer, qui vont devoir communiquer à travers des réseaux sans fil, méchés, parce que pour les mêmes raisons, on va éviter de tirer des fils dans tous les sens, surtout si on fait des objets connectés, dits des wearables. Donc il va falloir avoir des solutions de réseau. Et dès qu'on commence à toucher les problématiques de la réalité, il se passe tout le temps quelque chose dans la réalité. Donc on a des événements diffus qui arrivent, qu'il va falloir être capable d'attraper, de traiter en temps réel pour également adresser les problèmes qu'on appelle de big data, parce que c'est pas tout d'avoir plein de capteurs dans tous les sens, d'avoir beaucoup de données si on ne sait pas les traiter en temps et en heure. Donc la question, en fait, une des questions que je me suis posée, c'est quel type de framework peut être ouvert et évolutif pour l'intérêt des objets. Parce qu'il faut savoir qu'Internet a maintenant une quarantaine d'années, il n'a pas forcément été conçu pour l'usage qu'on en fait aujourd'hui. Et je prends le pari que ça en est de même pour l'intérêt des objets. Parallèlement à ça se développe l'informatique organique, où en fait on va qui s'intéresse au contrôle des systèmes complexes. Alors, une brève définition, qu'est-ce qu'un système complexe? C'est un système dont son macro-comportement est le résultat d'une émergence d'auto-organisation de composants d'interaction. Bon, pas de panique, si on prend une analogie chimique, on va avoir par exemple des molécules qui vont interagir, qui vont permettre la structuration d'un tissu cellulaire, qui va leur permettre d'échanger des informations, qui eux-mêmes vont pouvoir générer une couche neuronale qui va permettre de construire des réseaux de neurones et qui vont faire émerger une conscience. Donc à chaque fois, on a une organisation qui émerge, qui s'autostructure pour donner un autre support d'exécution qui va permettre, etc. Enfin, c'est un peu l'histoire de la vie. C'est très ambitieux, donc non, on ne traite pas de ça complètement dans cette thèse, mais c'est un domaine de l'informatique où en fait on va essayer de penser les ordinateurs différemment afin de leur donner ce qu'on appelle des propriétés autonomiques, c'est-à-dire leur capacité à s'adapter, à apprendre et évoluer. Pour faire ça, on change vraiment la façon de penser un ordinateur. C'est-à-dire que pour l'instant, un programme informatique, c'est principalement vu comme une recette de cuisine, où on va suivre une suite d'instructions séquentielles. Et quel est le problème qui se pose? C'est que s'il n'y a pas la bonne instruction pour s'adapter aux problématiques d'évolution de l'environnement, eh bien, le système n'est pas capable d'évoluer et il est programmé pour faire ce qu'il est pensé au départ. Donc en fait, on va essayer d'encoder cette information sous la forme d'interaction. On appelle ça l'informatique connexionniste plutôt que l'informatique computationnelle. Et ça nous permet de rajouter des degrés de liberté à notre système, qui va nous permettre donc d'avoir des propriétés dites auto-étoiles, telles que l'auto-adaptation, l'auto-déploiement, l'auto-réparation, enfin auto, tout ce qu'on veut, d'où l'étoile. Tout dans le cadre d'une approche bio-inspirée. Alors certains travaux s'inspirent par exemple du système immunitaire, d'autres travaux des réseaux de neurones, d'autres des modèles chimiques, etc. Enfin, il y a une panacée d'idées derrière cette recherche sur l'informatique organique. Et moi, donc, la problématique que je me suis posée là-dedans, c'est quel framework encore organique pour créer une intelligence ambiante, donc capable de gérer nos environnements dans lesquels nous sommes. Alors pourquoi cette thèse? Parce que je voulais proposer en fait un ensemble d'outils pour concevoir des intelligences ambiantes bio-inspirées, où en fait on va avoir une exécution à un niveau chimique, donc des éléments qui vont interagir et qui vont permettre la structuration d'un cerveau artificiel distribué dans nos espaces. Donc, plus concrètement, ça veut dire on va mettre 2 neurones dans chaque ampoule, 5 neurones dans nos radiateurs, une centaine de neurones dans notre smartphone, 1 millier dans la télé connectée. Et ces ensembles de neurones vont s'auto-organiser pour apprendre à gérer notre environnement intelligemment. Alors qu'est-ce que ça veut dire intelligemment? Ça veut dire d'une part optimiser la gestion énergétique, améliorer l'accessibilité aux personnes, leur protection, la sécurité, etc. Donc derrière, c'est un peu ces enjeux qui se cachent. Donc je me suis donc intéressé à 3 domaines d'exécution, un niveau chimique qui va permettre en fait de distribuer des flux de calcul d'informations à travers notre espace, un peu comme dans notre cerveau quand on a un stimuli neuronal, qui va permettre d'interconnecter une organisation cellulaire où en fait chaque objet de notre habitat, donc nos lampes, nos radiateurs, nos smartphones, nos télés, nos avatars intelligents si un jour ils existent, seront vus comme ces cellules qui vont donc interagir à travers un modèle chimique pour construire et déployer donc, des réseaux de neurones qui vont devoir apprendre à être intelligents. Maintenant, je vais poursuivre la suite de la présentation en anglais, puisque la thèse a elle-même été écrite en anglais et qu'on a le plaisir d'avoir le professeur Paradiso ici présent. So, who is EMA? EMA means Environment Monitoring and Management Agents. This figure represents the general overview of the architecture, which is based on a MapK architecture for monitoring, analysis, planning, execution knowledge. So basically we have our managed environment in which we have our different objects such as light, heating, smartphone and all of that. All of these objects will communicate thanks to a wireless sensor network together, and each of these objects will provide a set of services. So for example, a sensor will just provide the temperature information, and such thing, but your smartphone can provide us your next deadlines in your schedule. And all of that will be extracted by web services to provide a tuple space of resources which will be interconnected at a chemistry level. So a chemistry interaction, in fact, it's a web request between two web services. So this system has to be autonomous, and the question is how to manage that. So we have an upper level composed of supervisors. Supervisor can be our tablet or any services on the cloud. And the task is to analyze the behavior of our wired sensor and actor network in order to refine some application which has been designed by an expert or download from an app store or what you want in order to install them according to the requirements of our system. So now I will talk you about the organic IoT framework, which is composed firstly of the substrate based on a wired sensor and actor network, cellular level, which is an active resource middleware, the chemistry model for the interaction based on a proposal of augmented Petri network. I will resume everything by explaining how all of that is working with the metabolism and how to deploy and update the application on the system based on an RNA-DNA process modeled by reactive mobile agents, and then how to design, map, and deploy application before to briefly present you some experimentation to have a discussion on the best strategy to deploy that, and I will present you briefly the hardware and software that has been done during this thesis. So firstly, the substrate for wired sensor actor network, we have several challenges. The first one is, of course, the heterogeneity. Such as we have a lot of manufacturers, we need to find a network which allows them to communicate together. So to do that, I use Internet Protocol technology, which is used during the last 30 years. So it works very well. But we need also abstraction, because we need electronic engineer, we need network engineer, we need software engineer, and so we need abstraction to allow all of these engineers to work together. We have the challenge of scalability, because in a building we have several thousand of objects, so we have to have a solution to manage the scalability, and it's of course distributed spatially, but also in terms of software, because our object can require some software located on the cloud. So we have a distributed architecture, networked architecture between internet and the real world. And finally, we have the data management issue to know how can we change easily the information and in order to be flexible in our system. So now about the cellular active resources, I will explain you what is a service, what I call a service choreography on the right part here. For example, we have an object 1, which is able to know how many people are present in this room. And this sensor will provide this information to another one, the object 2, which is, for example, a brightness sensor, which will determine if we should turn on or off the light. And this object will ask to an object 3, for example, an energy management system, can I turn on or not the light? Or how much power can I use? And finally, the object 4 is our light. So this is a service choreography. That means that we don't have a central point to collect all information in order to control everything. I mean that each object has its own purpose and its decision process. More internally, we have here the general architecture of an object. So of course we have the hardware. We have a first abstraction based on quantity OS, which is a microkernel, which allows us to implement a pool of services which are networked and abstracted by a middleware. And this middleware abstracts all of that at a web service resource tuple space, such as each object can be directly accessible using a simple web browser. So we don't need gateway and any other proprietary protocol, which was my first challenge. In EMA, we have 3 default services. Everything is done to build new, but we have 3. The first one is S for system. These services provide information on the node, so the root to internet, the list of neighbors, its configuration, its semantic definition, and the list of internal resources. We have another services called L for local. Local is the storage services, which is used to store variable or file. And finally, maybe the most important, A, for agents. An agent models the interaction between two objects. According to the current context, resources context of the node, an agent will emit a request to modify another resources, which will modify, and these resources can trigger another agent. We will modify another resources. We can trigger another agent. That's how is working the dynamic on the system that we can see here. This agent modify these resources, which will trigger this agent. We will modify these resources, etc., etc. So this is how is working the dynamic of the system. If we take a point of view of this architecture and we cut here, we have an abstraction. We have we can model that like a proposal of augmented Petri network, in which each places is resources, and the transition are the agents. So we can, in such situation, control the system resources P1 according to the system resources P0, thanks to agent T0. Such as an agent is also resources in the proposed model. Each transition is connected to virtual link to a places which allow us to modify it. So, to present how it's working, when we modify the value P0, P0 is different from P2. We will store in P1 the value P2 minus P0, and when we store this value will be pushed on P2, which will be stored from P2 minus P1. This loop is a stochastic gradient calculation defined here, which is the atomic element to train a neural network. What we can observe here is that we have another agent, T2, and this agent is triggered when the value of P1 is greater than 50. And in such situation, you will delete everything. This agent can be viewed like a control system to be sure that the system will not go on an unauthorized behavior. So if the value P1 is reaching an unauthorized value, the system is uninstalled automatically. So to resume about mechanism, we are different agents with different abstraction, which are interconnected by service choreography, which can be composed. So in such situation, we have the service choreography NS0, which assures the connection between NS1, NS2, and NS3. And for the security purpose, I propose to encapsulate that in a namespace secure by encrypted IES key, such as each resources as it's to communicate with another one. We use a security key, which will be also used by the target to encrypt the information. Why? Because if a hacker succeeds in corrupting one of the namespace, he cannot corrupt the integrity of the system. So okay, so now how to deploy application? I propose the RNA DNA process. So what does it mean? For example, we want to deploy this distributed application. So we want to push P0 on the node 0, and P2 on the node 2, and P1 on the node 3. And here we have the network routing path. So to access to the node 2 from 0, we need to cross 1. This can be a very challenging large-scale network, because of course I can deploy that by sending directly to each node the good agent. But we can have a network conjunction on 1, because all communication will across 1, which is a real problem. So to do that, I use the property of the proposal of agents. An agent can modify another agent, including itself. So it can carry other agents to install other agent or itself. So based on that, we can build a big agent that we will launch on 0, and when you arrive on 0, it will install P0, and install the agent D0, and once the agent D0 is installed, it is triggered in order to launch on 1 the agent D1 and the agent D2, which are automatically triggered in order to install on 2 the agent P2, and the agent D2 will install the agent P1. So to resume, we can think that like a dynamic network agent carry other agents in order to install them, such as a final graph of residual network agent of service choreography. This is one way to do that. But we can have another strategy with this model, which is based on mobile agents. Because an agent can make a copy of itself to another node and delete itself after that. So we can build a big agent which contain all our agents, and like ant, like the stick merge in ant algorithm, we move from node to node, and according to the local resources and the requirement of the node, install what is needed. So this is a two-way to deploy based on RNA DNA process. So how to design, map, and deploy application on that? Firstly, we have a functional view in which we can design templates in order to simulate the behavior of our service choreography by using the Petri network. And we have to instantiate this template, such as, for example, if we design a control command for the light, we have to deploy this application for each light present in the building. So we have to duplicate it, and this duplication will generate an instantiate graph. And according to the target of our system, of our object, the big question is to know how to map that in order to minimize network communication. This can be viewed like a multiple choice snapshot. So each object is a bag in which I can put a given number of red box, a given number of green box, blue box. And the question is, what is the best distribution of green, blue, and green box among the different bags in order to minimize the communication? This can be successfully resumed as a pseudo-Boolean optimization with a set of constraints. And the experimentation shows that the number of constraints increases linearly with the number of nodes, and it's not dependent of scope, which induces that we have an exponential time of resolution during the mapping problem. And that's a big problem. So what we can conclude with that is, if we want to map all service choreography over the building, we firstly have to map each room, then each floor, then the building, to manage this complexity issue. The bottom part here represents experimentation on the DNA-RNA process that I presented you previously. In this case, it's the matryoshka, so the composed agent. Each agent contains another agent. So the green bar represents the agent payload size. And the different curves, the different time, writing time, transmission time, execution time. With the composed DNA, in this case, this agent will upload 40 nodes in order to install the service choreography. This is very interesting when we want to make a chirurgical operation to install a given service choreography in a given locality of the network, because we will build a big agent and we launch this agent to the local area of our network, and it will be executed, the installation will be executed in the area instead of remotely. And so we avoid to consume too much network. However, this is very bad if we want to install several times the same application on several nodes, such as we have a redundant information, because it's a composition. So at each composition, we have a redundant information. So another strategy is to use a self-deployment DNA-RNA. So a big agent will contain one sample of each agent that you have to deploy, and this agent will across all the network, for example at the initialization, in order to install common service choreography in all nodes. For example, when we start the system, we have nothing. So we have at least to populate the different nodes with the service choreography to discover the services. If we don't know that a node exists, we cannot manage it. So we will build a service choreography which allows each node to push its information to the supervisor, and we have to install that on each node. So we build a self-deployment agent that will launch, like an ant, move from our bees, from node to node to node to install everything. So to present the software design, here we have the designer application. In the left part, we have an example on how to design an application and to simulate the behavior of a Petri network. In this case, it's a very famous problem in distributed computing called dynamic philosopher problem. And then when we validate our design, it's working as we want, we have to map that on the target. And this is the part of this second window, which will determine how many times we can duplicate, install this application according to our requirements. And the output of this mapping is a composed agent, the DNA agent that we will launch on the network. And to simulate that, I do that based on the Kuja simulator, in which I developed some additional plugin, in which we can visualize the execution at software and electronic level on the deployment of our service choreography over our network. So now I will present you the intelligent part of EMA. Which is two components. The artificial neural controller. It's a system which have to learn how we use our environment. That means when I arrive in a room, I turn on the light, and I would like that the system remembers that in such situation, the light should be turned on. So this is basically what is done by this component, and the other one, the neural voting procedure. Okay, I have several action neural controllers able to learn how to control a lot of things, but if these components share common parameters, such as energy, for example, I have a system which is monitoring the loading of my electric car, and I have another one for the heating, and I have a strong energy constraint because it's very expensive. I have to have an arbitration to manage that. This is the purpose of the neural voting procedure. About the artificial neural controller, how to statistically and empirically learn, how to use statistical and empirical learning to control dynamic and open environment. So basically we have our space, managed environment, in which we have a set of actuators, a set of sensors, and some human action. And the system have to learn some behavior according to the current context of sensing and acting, and the human action, what should be done. Such as the system can have several modes. For example, when I'm at home, I would like to be in a comfort mode. When I'm leaving my home during a long time, because I'm on holiday, I would like to have another behavior, etc. So we need to learn several behavior, and we need a controller which dynamically know which one should be played. In terms of neural point of view, this can be viewed like that. Here we have our input context composed of the sensor value and actuator states. This input context will be presented to our different behavior called classifier, and this classifier will learn the output in order to change the state of the actuator. So this is a loop, so we have to learn two things. Firstly, we have to learn the transition, of course. In such situation, I have to do that, but I have also to learn invariant transition. I mean, if I'm in a good state, I have to stay on this state, because it's living, it's a loop. So, how to learn? I use a simple update chain, very classical in machine learning, called stochastic gradient descent, that I present you the initial model on Petri network to do that. So basically we change the synaptic weight, W, according to the quadratic error between the automatic control and the human action. So when we do that, for example here we have an input, a simulation of input context in which we have a 5 sensor and actuator. And the system has to determine how many neurons is required to learn that. In this case, it's 6 neurons is enough. And then when we play the same context by adding some noise, the system has to predict correctly the next state without the noise. Okay, so when we are able to learn a behavior, the question is how to schedule the different behavior. So basically here we have input stimulation, in which we have a simple counter, Fibonacci suite, some noise, a random state machine, and according to the context, when the system is running, each behavior will try to predict the next state. And if one behavior succeeds several times, that means that it's probably the good behavior, so it will be scheduled here. But when none of the behavior are able to predict the next state, because we have too much error, this is the output error of the different behavior, the context input is extracted in order to build a new classifier, a new behavior, dynamically, which can be loaded. So next time when we present again this context, the new behavior is displayed. But is it a good idea to use several behaviors, several classifiers? To evaluate that, I do a simple experimentation in which I use a linear transition function and quadratic transition function. For linear, we need one layer of 20 neurons. For quadratic function, we need 2 layers of 20 neurons. So if we learn in 2 separate classifiers, we need 60 neurons. But if we want to build a big one, we need 3 layers of 60 neurons. So 180 neurons versus 60. So that makes sense. But if we think our brain is designed at biological scale, we have specialized areas interconnected by other specialized areas. It's not an homogeneous structuration in the brain. So that makes sense mathematically that we find the same result. So to resume in EMA, how it's working this job. Initially, we would like to have a default behavior, or to be able to program our behavior. So we can use a graphical space in order to infer symbolic rules, or we can directly write symbolic rules for geek. And these assembly calls will be used to generate a statistical training program in which for each possible context input composed of actuator state and sensor value, we will provide the response to provide. And actually, when we have a neural network which has been trained, we could be interested in knowing what has been encoded in the neural network, what is the behavior. So we can play all these possible input of our neural controller in order to generate the response, which will build a statistical response space in which we can infer symbolic rules that humans should be able to understand. Of course, this information is lower than this one because in a neural encoding we can store a lot of more information that we can express with some word. So to resume the general methodology, we have two parts. On the supervisor part, we firstly have to define some stationary rules in order to generate a training program which will be used to train a behavior. This behavior will be deployed on the active resource middleware, so on the object. And this object will execute this behavior, and according to the human action, each time that human operates an action, that means the system is wrong. So we have to learn. So the data, the context input is extracted in order to refine the training program, which will be used to learn again and to deploy again and execute continuously. Initially, this action neural controller has been designed to be executed at the chemistry model. However, I explained we need 16 neurons for a simple linear and quadratic function. So we need 60 resources to store the neuron activity, 60 agents for the transition, and 60 other resources to store the gradient value. So 180 resources, which is obviously too heavy for a microcontroller. So I change the way. I use the modular architecture of EMA to build dedicated services to execute this neural network, in which we will just push the neural behavior as resources. So one resources this time is just one behavior. And these services, according to the input and the behavior, will generate an output vector which will be connected to the other resources at the chemistry level, such as light, heating, what we want. Okay, so now we have our action neural controllers. The question is, what happens when they share some common parameter? I give the example of the energy. So what kind of distributed consensus for the arbitration of shared parameter? What is interesting in this question about wired sensor network is that we have to propose a fully distributed approach, such as I explained for a scalability problem. We are constrained about energy, so we are constrained in terms of computation, so we can use only elementary computation, and because of the energy constraint, we are also limited about the network, so we have to find an elementary protocol to do that in order to limit the network load, and of course the algorithm should be scalable, because if it's not scalable, we don't have the problem. So among the different possibilities, I was particularly interested in voting procedures, such as this democratic. And among the different voting procedures, I focus on the range voting procedure, such as is the less manipulable to elect somebody. How it's working? We have our agents will define the preferred order among the different choices, and according to the ranking of each preferences in their preference order, this preference will get a score. When we obtain that, we have an aggregation step, which consists in this case, for example, just to sum, to build a new, what we will call the utility function, which will give us the new order. So in this situation, C1 and C4 get the same score, so they are equivalent. C1 is equivalent to C4 for the community, but are preferred than C3 and C2. So how to do that by fully distributed approach? I'm interested in network average consensus, such as is very close of the gradient descent used for the training of neural network. How it's working? Each agent will broadcast to its neighbor its utility function of its preference order. And when an agent receives the utility function of its neighbor, it will modify itself according to the gradient value of the utility function that it receives. At the end, this algorithm converges at an alignment property. That means that each agent will converge on the same utility function, on which we can apply a decision function. So that means that the decision is not taken by one big boss. Each agent will aggregate its utility function with the other one, and because we are sure about the aggregation, each agent can take its own decision and be sure that everybody will get the same. However, we have a problem because this is an iterative algorithm, so we have an accuracy issue. So when are we enough accurate to be sure that the decision will be consistent? A mathematic deadlock avoids us to do that. We cannot determine the epsilon parameter, such as it's depending on the network topology and the initial preference of each agent. So the strategy is to fix a given epsilon, play an aggregation, and the agents, according to the space between the value of their utility functions, they will decide if they have to do another aggregation with a lower epsilon value, etc., etc. To illustrate, we have here 25 agents with their own utility function, which are aggregated here. So for the aggregation, we need 50 iterations to aggregate and to reach a final utility function of preference according to an epsilon parameter. What is the value of this epsilon parameter? It's provided here. It's 10 power minus 3. And the aggregation process has been operated 3 times. So the first time, the estimation error of each agent decides that, okay, we are not enough accurate, so we have to do it again. The second time, it wasn't enough again. But the last one, it was enough to be sure that all agents will take the same decision. What is interesting with this algorithm, it's about its complexity, such as the complexity is linear according to the number of agents, which is a very good property in distributed computing. And it can be fully implemented at the chemistry model of EMA. Based on network average consensus agent, we will assure the aggregation. Then an aggregation agent, we will determine how many times the aggregation should be operated. And then a selection agent, we do the decision. We make the decision. So now I will present you my work at MIT. It's not directly connected to EMA, but it's using the same skills about neural technology. So firstly, I will present you the Tinmarsh Living Observatory project and the concept of close reality, my job, and my contribution. So Tinmarsh Living Observatory is a common project of the Responsive Environment Group headed by Joseph Paradiso. And it's interesting in studying the restoration of a cranberry farm into its initial state of marsh in order to analyze the complex interaction between the different ecosystem scale at bacterial, vegetal, wildlife, and climatic in order to validate theoretical models or improve them thanks to in vitro technology. What does it mean? That means we have a set of sensors on the site, microphone, camera, a lot of things, and we want to understand how we can help nature mother to come back. Because it's not because we want to help her that we will really help you. So the challenge behind that is to understand this complex interaction. Instead of using traditional approach of data analysis and dimension reduction that we can see in data scientists, the group is interested in the concept of cross reality. It's a merging between real world and virtual world. So that means we have an environment simulated which is rendered thanks to the real-time information provided by the different sensors in the site. And as we can see, it's very close. So inversely, the interest is that when we are in the virtual environment, we can across it, of course, we can navigate over time. But when we are on the site, we can use augmented reality, such as Google Glass, for example, to get information on how was what we are looking previously. So this is a merging between reality and virtuality. My task was how to detect and geolocalize wildlife in the Tinmarsh virtual reality. That means among these different strategies, we have to use the microphone. So it's to be able to recognize on each microphone what kind of bird, what kind of animal we can listen. So as you can see, it's very different for a human. A big animal, we have blue jay, crow, sparrow, frog, it's very different. And traditionally, we use machine learning techniques with self-handed feature extraction. What does that mean? That means that on the signal we will extract relevant information and we apply machine learning on that. So it's working well for simple processing. For example, for our check bank, it's what is used. We have simple to recognize digits, it's working well. However, for sound analysis, it's very more complex, as we can see. So I decided to use a new approach in machine learning called the deep learning. What is the idea between deep learning and instead of figure out how to classify something, we will firstly determine how to represent this thing. For example, for our visual cortex, before to be able to recognize a bottle, we have to be able to recognize line, circle, color, and this detector, which has been learned during our evolution, will modify the initial information provided by our eyes into a new representation state called feature. For example, with this, by presenting a picture of something, some of this detector will be activated, we will generate a new picture, a mental representation of something. And this mental representation will across an audio feature space, which allows us to represent more complex things, like for example cycle, scare, balloon, and all of that, and which will across a third one, which will help us to recognize texture, perspective, mobility, and all of that. So it's very, the question is what is the best representation of something in a different abstraction level. So for picture processing, the convolutional neural network are very efficient. So these pictures are extracted from this paper. However, I'm working on sound. And on sound, it's not the same thing. So I have to figure out another way to do that. And I was particularly interested in a restricted Boltzmann machine that will be used. The purpose of a restricted machine is to find a way to make a reconstruction of the initial information. It's like when we learn to draw, we observe something and then we try to draw the same thing. That's the same idea about restricted Boltzmann machine. And so we will build feature space in which we will encode the information, so we'll get a mental representation of the information, and from this mental representation we try to reconstruct the initial image. And we will stack all of that to have higher abstraction level. What does the synaptic waves look like in the learned feature space? In this example, this is the first layer of feature, in which we have 64 neurons. Each neuron is represented by a scale, and has learned a particular feature of the human voice. For example, here this line on the middle is a fragment of our voice, which allows us to know if a man or a woman is speaking. And the second harmonic, for example, here, such thing correspond to our timbre in our voice. And so when a sound is presented to the system, some of these neurons will be activated and will be presented to build a new picture, and will be presented to a second layer composed of 30 neurons, which will give us the information, this is a frog or not, this is a human or not, this is a blue jay or not. How to dynamically build a new knowledge in such architecture? The project is called TILMAF, so it can be viewed like a virtual sensor. We get the audio stream from an IceCast server, and this audio stream is has a FFT encoding, and then is filtered. And it's presented to the neural classifier. Each classifier will provide us the probability that there is a frog, or a human, or else, including nothing. It's important to know what is nothing. And if none of these classifiers, including nothing, is able to say there is something, this input stream is recorded in order to build a new training program, which will be used to learn a new classifier with a pre-training step to extract the feature space. Will be transformed into a feed-forward neural network, which will be trained for the classification task, and if it's good by cross-validation, is loaded dynamically. This is a screenshot of the TIDZAM web application. Here we have two microphones, for example, and we have a pool of classifiers here, and we have here the probability that there is a bird whistle, here there is nothing, there is a frog here, all of that. On the left part, we have the event distribution of prediction. So the system is stupid because most of the time it don't know what is it. But sometimes it says there is nothing, and there is some frog, some bird whistle, and all of that. So that means that this system has to learn a lot, again, with the loop of extraction. Donc maintenant je vais conclure en français. Donc en termes de contribution à mon sujet qui s'intéresse à proposer une influence ambiante organique dans le monde code et EMA, j'ai proposé donc du contenu théorique avec un framework pour concevoir un état des objets organiques. Deux modèles donc théoriques mais qui ont été implémentés en vrai de contrôleurs neuronaux distribués et une procédure de vote neuronale distribuée. En termes de réalisation matérielle concrète, il y a eu donc le middleware qui a été implémenté pour concevoir des objets connectés très facilement et les intégrer à l'intérieur des objets avec des aspects de sécurité. Bien sûr, alors là, je me suis fortement basé sur QGIS Simulator. En fait, j'ai développé des plugins sur QGIS Simulator qui permettent d'avoir une meilleure analyse du système. On a développé un logiciel pour concevoir la chorégraphie de service, la simuler, les mapper et les déployer. Enfin, il y a eu le projet TILSAM du MIT. Et j'ai également conçu une plateforme électronique dont il y avait la photo mais dont j'ai oublié de vous parler. Au MIT qui permet donc d'exécuter EMA dans le monde réel, c'est pas juste simulé, et ça marche. Donc en termes de difficultés et d'intérêt, ce que j'ai trouvé d'intéressant, de positif dans ce travail, c'est d'avoir pu construire une métaphore bio-inspirée, ce qui n'est pas toujours évident parce qu'on arrive toujours à un moment. En fait, elle s'est faite a posteriori, c'est-à-dire c'est pas donc faire ces métaphores filées avec des contributions multidisciplinaires. On a du réseau, de l'électronique, de l'architecture web, de l'intelligence artificielle, etc. On a proposé du contenu théorique et pratique en intégrant des approches robustes. Par exemple, quand il s'agissait de faire un réseau de capteurs, l'IP ça marche depuis 40 ans, donc je ne suis pas allé chercher plus loin. Je prends ça, les réseaux de neurones, etc. À chaque fois, j'essaie de prendre ce qui me paraissait le plus solide pour construire quelque chose que je souhaite durable. J'ai eu des difficultés à valoriser mon travail étant à la croisée des chemins. C'est toujours difficile quand on a une pool d'experts en face ou quand on est dans une communauté d'experts et d'arriver. Je ne suis pas expert dans ce domaine-là, mais regardez, ma contribution c'est de connecter votre domaine à d'autres domaines et bon, c'est pas toujours évident de présenter. Surtout quand on n'a pas le vocabulaire qui va bien, parce que par exemple pour l'histoire des connexions des réseaux de capteurs, si je parle à quelqu'un qui fait du web, je vais parler de ressources, si je parle à un mathématicien, je parle de places, et si je parle à un neuroscientiste, je parle de neurones. Donc bon, il y a un moment où on s'embrouille et je sais pas trop me placer. Et malheureusement, j'ai pas eu l'occasion, alors peut-être ça viendra, j'espère, de faire une application réelle sur des vraies données avec dans un vrai cadre, ce qui pourrait être sympa. Donc en termes de future work, c'est pareil. Ce qui pourrait être rapidement fait, en fait, c'est de combiner l'exemple que je vous donnais d'arbitrage énergétique entre les différents contrôleurs neuronaux. Où, par exemple, on aurait un système de chauffage et puis un système qui gère la charge de la batterie et d'assurer l'arbitrage énergétique entre ces deux systèmes qui auront appris quel est le meilleur moment pour charger le chauffage, etc. Donc ça, je pense que c'est quelque chose qui peut être rapidement fait, mais voilà, il y a un moment où il faut arrêter ça, mettre en point. Mais c'est future work. Et enfin, en termes de TILSAM, bien sûr, c'est déployé sur un grand nombre de microphones. Il y a tout un travail de refonte pour améliorer les classifieurs parce que on s'est rendu compte que quand il pleut, quand il y a beaucoup de vent, etc., le système peut détecter un peu tout et n'importe quoi. Donc il y a déjà pas mal de pistes sur comment on va faire ça, qui vont être en fait encapsulés dans ce problème-là, parce qu'en fait, quand on essaie de distinguer différents types d'oiseaux, c'est marrant de voir qu'on ne peut pas distinguer les oiseaux à travers leur simple timbre, parce qu'ils chantent. Et que certains oiseaux, pour les distinguer, la seule façon de les distinguer, c'est de les écouter durant une longue période de temps pour reconnaître leur chanson. Donc sur certains types d'oiseaux, voilà, l'approche focalisée sur le timbre de la voix ne suffit pas, donc on va changer ça avec une approche stochastique. Et voilà. Et enfin de faire une évaluation quantitative, parce que ce travail a été réalisé en 3 mois, et donc on n'a pas eu le temps de mettre en place une expérimentation digne de ce nom. En termes de publication, ça a donc donné lieu à trois conférences. Un journal qui présente l'approche générale de la thèse en informatique organique. Actuellement, il y a un autre journal qui vraiment présente le framework EMA pour concevoir pas seulement de l'informatique organique pour le coup, mais de façon plus générale, comment est-ce qu'on peut concevoir des architectures de web services distribués dans le cadre des réseaux de capteurs, dans un tas d'objets. Et j'ai été invité sur le papier qui présente le projet général TILMarche. Je suis invité par Joseph Paradiso pour ma contribution TILSAM à ce projet. Et je vous remercie pour votre attention.
Merci Clément d'avoir occupé si brillamment le temps qui t'était imparti. Il a occupé parfaitement. Tu vas pouvoir te réhydrater. Merci de nous avoir rappelé que les oiseaux pouvaient chanter. On l'avait oublié à Paris depuis plusieurs semaines. Et la pluie génère tout le bruit qui vient à nos oreilles au détriment de celui des oiseaux. Alors, suite à cette présentation, tu vas pouvoir échanger avec les membres du jury et à commencer peut-être, si tu t'es bien restauré, par les rapporteurs qui ont étudié d'encore plus près que les autres membres du jury ton travail et vont pouvoir t'interroger. Alors je propose que M. Frédéric Weiss, qui est maître de conférence habilité à diriger des recherches à l'université de Rennes, qui fait sa recherche à l'IRISA, prenne la parole le premier pour échanger avec toi sur les contenus scientifiques de ton travail.
Ok, merci. Je ferai quelques remarques en français, puis ensuite then I will switch in English for questions. Donc, je l'ai mis dans mon rapport, mais je tiens à le souligner, hein, je suis assez impressionné par la quantité de travail que tu as abattu en termes d'implémentation surtout. Alors on sait que l'implémentation normalement n'est que le résultat de la thèse, mais pour travailler aussi dans le domaine de l'IoT et essayer depuis plusieurs années d'implémenter des choses cohérentes sur des nœuds qui sont contraints à tous les points de vue, avec des modèles de développement qui sont complètement balbutiants. Quand on regarde ce dont on dispose dans le domaine du génie logiciel et quand on regarde ce qu'on a sur un nœud quantity, ben, il y a encore un gap absolument gigantesque. Donc que tu aies réussi à faire fonctionner quelque chose sur des environnements sur lesquels finalement peu de gens travaillent à l'heure actuelle, et que ce soit aussi cohérent et qu'à la fin ça fonctionne, je tiens vraiment à le souligner parce que c'est un travail qui est considérable. D'autant plus que, je ne sais plus, on l'évoquait tout à l'heure, on s'était rencontrés il y a quelques années et tu m'avais présenté ce qui était
Emma à l'époque, l'idée.
Emma de l'époque, et j'ai été très surpris, mais agréablement surpris de voir ce qu'était devenu Emma, au départ d'une couche middleware qui masquait une certaine complexité protocolaire, une vraie approche et un vrai modèle de programmation. Parce que je pense que c'était un des objectifs, c'était d'arriver à un vrai modèle de programmation, et tu as vraiment proposé des pistes intéressantes. Donc bravo pour ça. Et pour y toucher aussi un petit peu à l'aspect multidisciplinaire de l'IoT, je sais combien c'est compliqué de publier entre plusieurs communautés qui désignent exactement la même chose mais avec du vocabulaire différent. Ne serait-ce qu'en l'IA distribué, les gens de l'informatique distribuée, on parle d'un côté d'agents et d'un autre côté de nœuds communicants, donc c'est compliqué. Donc là-dessus aussi, bravo, parce que c'est quelque chose qui n'est pas simple. So I have a first question about routing, because in my understanding, your deployment process follows the network routing path.
Exactly.
Okay? And in my experience, we have a lot of problems of stability in routes. So during the deployment process, how will your agents react? If, for example, if you have a reconfiguration because of Ripple has detected that you have a weak link between two neighbors that becomes weak, how do you manage this reconfiguration during software deployments?
Right, it's a very challenge in OS sensor network is how to manage the reconfiguration of the system. Firstly about network, I dedicate this task to Contiki. This is my initial abstraction. Mm-hmm. However, I start with that. In Emma, actually, to make experimentation, I have a dynamic routing and with a very frequent reconfiguration to change the route. But because when the node, we stay on the same wired sensor network, so when we have a reconfiguration, we keep the same network prefix. So we just have nothing change, just the route organization. And for the agents, what can be, how the system will detect that. If we have, for example, a topology in which we have we have this initial topology, for example, so this is our link. So of course, when we will deploy our first service choreography, the mapping system will detect that an agent should be pushed, I will change the color, that the service choreography should be something like that. So we will deploy some agents here. And when the routing, because it's not stable, will change, for example, for something like that, of course it's not efficient, because this communication should be operated like that. So firstly, the quality of services will be maintained because the agents are only take care of the IP, so the IT don't change, only the efficiency of the communication. What will be observed is that I told during the presentation that at the initialization we will install service choreography. And this service choreography will send this information route. And so once the routing will change, these resources will be changed. And so the agent of service discovery will be triggered and push the information to the supervisor. And so firstly, the supervisor will know that the network topology has changed. And he will decide if, or for now, he will each time recompute a new mapping and to build a new deployment.
But the answer was.
But I think that we have a cost function in the software to determine if we should or not deploy that.
Okay.
So we have a cost function, so we can define any metrics. By default, it shifts time.
So finally, the action is atomic. You have the ability to decide if the action between the both agents can be triggered or not.
Mm.
Okay. I have also a very classical question. It's about energy.
Yeah.
Because we have a lot of works in wireless mesh networks using 6LoWPAN and embedded nodes with Contiki or Riot. And in my experience, I have already made a lot of experiences using this kind of platform. And honestly, when you use software deployment mechanisms on a mesh network, each node has the ability to live on a few hours. So in my view, this kind of deployment is not realistic, for example, in a building. What is your opinion about that?
I will speak about the story of Emma. Initially, that was the first question. Energy, and I was thinking how to avoid to consume. I have to sleep most of the time. So in Contiki, we have Contiki Mac, for example, we just trigger, wake up 1 millisecond, send a request to know if the node has to do something and go to sleep. But what is interesting in this approach is because it's event-driven. I mean, if we design a software by an approach event-driven, if there is nothing happen, the system don't do nothing. So that was the idea of this service choreography. If this object don't emit anything, the other one are not doing anything, so they are just sleeping. And so, of course, up to fully answer your question.
But what do you mean by sleeping? Because if you consider the operating system level, behind the term sleeping, you can have a lot of mechanisms.
This is the big question that it's in a white box because I dedicate that to the wireless sensor network community people. But what I can see about my task is that all of this is consuming nothing when there is nothing to do. There is no permanent loop. So in Contiki OS, of course, you have the same design with Contiki Mac, for example, but as you said previously, it's not very stable. But I hope that soon this will be stable, and there are a lot of people working on that, so we can assume that in next year this will be. And if this part is fully event-driven, all the system will be event-driven, and the application over the wired sensor network will be event-driven. So everything will be event-driven, which is the idea here of my presentation when I said distributed event-based software, which is a very challenge to do that, to be able to diffuse and to manage the information. Of course, I told about big data, but energy is the main point in the building.
So in my understanding, the MR layers have the ability to sleep completely. And
I think it's more than that because it's not sleeping. It's like a mechanism. If you have nobody who turns the road, there is nothing happen.
Okay.
So it's not sleeping. You don't have a loop, an eternal loop. You say, oh, I have nothing to do, I sleep. No, it's you need a stimuli, like our neural brain when the brain is dead because you have no stimuli. But if you have a stimuli, we have a thinking.
Okay, it's clear.
That's the idea.
I have another question about communications between nodes. So, why using co-op? Actually,
I don't know.
because just to be clear, using co-op is very interesting. For example, if you want to publish something, but co-op is very good when you have a client and a server. For example, the main idea of co-op is that you can develop an IoT application like a web application. So from this point of view, co-op is very useful and very efficient. But when you look at the internal architecture of an EMA node, it's not a client, it's not a server, it's an hybrid node.
Mm-hmm.
And it's very near from a peer-to-peer architecture, actually.
Exactly.
So I'm not sure that implementing a client, co-op client, co-op server in a so constrained node is the best solution. So how could you improve that? And have you tried to develop something more specific for your environment?
That's funny because yesterday when I came here, I talked briefly with somebody about the architecture. He said, "Oh, it looks like blockchain." Yeah, we can do a blockchain with that. Why I use COP? In fact, COP is for me just an encapsulation. The real model is the agents, and an agent is just an interaction rule, if, then. So I can encapsulate that in anything. Why I use COP? Because thanks to David Manga, he told me heterogeneity should be managed, web services, and right. And I think this is, I think that an object should be viewed like a website or a web services interface. At least for the normal evolution of Internet 1.0, the Web 2.0 cannot exist without digital content. So the 2.0 is built on 1.0. So it makes sense that for me that the 3.0 is built on the 2.0. So in this logic, I have the feeling that we should use web services. So of course, I think we definitely can do something more efficient about EMA implementation, and maybe we will do. But in fact, for now, the whole EMA engine here is use 800 bytes of RAM memory on 10 kilobytes of footprint memory, which is exactly the same thing than Quantity OS itself. Okay. So we have, for now, there are other challenges for me about managing all of that. But of course, yeah, it's definitely not the most efficient way to do that.
Just one small technical question. You speak about a tuple space for agents.
Yeah.
So for me, tuple space is used for synchronization between processes. It's not clear what exactly is the objective of tuple space.
That's something that I wasn't able to. Thank you. If we think this, we make the abstraction at the orange. We can visualize that like a distributed associative memory. That's why I talk about tuple space. It's like a memory in which we will make link and abstracted by the network. So that's what I call the tuple space, like an associative memory.
Okay. One last question. Have you planned to publish the EMA code as
It's open source, it's on my GitHub. It's open source since last week, so anybody can download it, install it, and play with it.
And with support?
You're welcome.
We support.
And one last question. I think it could be a good idea to publish something in the software engineering community, because actually we don't know exactly what is a middleware for IoT, and I think it would be a good idea to present something like a part of your work presented as a middleware and as a programming model for IoT. That's just an advice.
Okay.
So, thank you very much.
Merci beaucoup, Frédéric. Nous connaissons déjà au moins une brique de ce middleware de l'Internet des objets. toute entité a le droit de dormir pourvu qu'elle ne consomme rien. Je fais bien, c'est ça. Très bien. Et il faudra continuer, bien sûr, à décrire les autres actions. Nous allons maintenant donner la parole à Madame Salima Hassas, qui est professeure à l'université Claude Bernard à Lyon 1 et qui a étudié sous d'autres aspects encore son travail de recherche.
Merci, Monsieur le Président. Tout d'abord, je remercie M. Cyril de m'avoir invité à ce jury. Je suis ravie d'être là, d'autant que ça m'est revenu la dernière fois où je t'ai vu, c'était
À peu près la même époque.
Oui, c'était en stage de DEA, je crois.
Ouais, c'est ça.
À l'EDF, et tu étais passé nous voir dans
Exactement.
Quand j'ai lu la thèse, je n'avais pas cette information. Donc, je suis d'autant ravie d'être là parce qu'à l'époque, j'avais beaucoup apprécié les échanges avec toi et j'avais vu déjà ton esprit brillant que je retrouve au niveau de cette thèse. Donc, je dois dire en anglais, I love your work. Mais je reviendrai après. J'aime beaucoup le travail, j'aime beaucoup surtout cette vision que tu as essayé de donner à ton travail, qui est cette vision systémique. Moi j'aime bien les choses systémiques. Donc c'est quelque chose de risqué, et j'ai trouvé que dans ton travail, tu as su bien manœuvrer pour bien t'en sortir. Parce que quand on s'adresse à des choses, il y a des rétroactions de partout, des interactions à différents niveaux, différentes disciplines. C'est pas toujours évident de s'en sortir, et je trouve que tu l'as très bien fait, aussi bien au niveau du travail, donc je suis aussi impressionnée par la quantité du travail que tu as fait, qu'au niveau de la rédaction du mémoire, qui je dois avouer était vraiment, ça a été un plaisir pour moi de lire ce mémoire. Même pour les parties qui sont couches basses, où j'avoue, mon niveau de connaissance est assez limité, j'ai appris beaucoup de choses. J'ai pas tout compris, mais voilà, j'ai appris énormément de choses. Donc ça c'est sur l'aspect mémoire et travail de façon générale. J'avais, bon, enfin je ne reviens pas sur le reproche, j'avais fait deux, trois petits reproches sur le mémoire qui était sur la manière, sur la partie état de l'art, je trouvais un petit peu, c'était un peu cohérent, c'était un petit peu frustrant de voir avec la quantité de choses que tu as fait, avec la quantité de domaines que tu as maîtrisé, parce qu'il y a vraiment une maîtrise des différents domaines que tu as touchés. Je trouvais dommage que la partie état de l'art soit un peu courte, un peu. Ça manquait un peu de synthèse. J'ai dit la même chose aussi au niveau de la conclusion, mais là, tu t'es bien rattrapé au niveau de la présentation. Donc je te félicite aussi pour la présentation qui est claire, limpide, synthétique. Donc, ceci étant dit, je vais passer à la partie questions. Alors pour les questions, je passe en anglais, moi aussi. Okay, so I switch to English for our questions. Okay, I have different questions, but my questions are not hard, so sometimes they are very high level questions and sometimes it's low level. The first one is related to this concept of agents. So this is my area. So when I see our system, I wonder, why do you call this agents?
That's a big question. Because it was an integrative approach. So initially an agent was a node. Then after that an agent was a functionality, not more a node. So we build an abstraction. And then after that I refine the granularity and say, oh, an agent is composed of interaction. So I have also agent reactive in the literature. And I was not agree regarding the different agent definitions in literature to call my node or other like agents, because it's not really cognitive, it's not. And so I don't, the only agent definition that I have the feeling that I can use in my work was at the interaction agents, because I'm well afraid and people say, hey, it's not a cognitive agent. Yes, I know. So.
Yeah, the question is not related to. I think definitely you should avoid to use intelligent agents, because there are not, there is no intelligence. The intelligence is in the system, but it's not in the agent. This is the first one, and the second one is, but this is a question of terminology. My question was about the. Can we imagine in your system that there is a behavior, autonomous behavior of agents? Here, your agents are pre-programmed, so you have this sequence of action that they have to do, and you have, for example, for deployment of agents. I'm not in this part. For consider the slide number 10. You use agents to deploy code. But what is done is that agents are, it's a sequence of procedure triggering.
Computation
right?
flow.
Yeah, it's a
Distributed,
computation, but
exactly.
it's completely guided by the design of the high level. Could we imagine in your system that to face robustness problem, for example, if you have change in the architecture, there could be some feedback from the system to retrigger the dynamics.
Yeah, I think that's to reprogram the system. So traditional Matkey architecture or agent design, this can be viewed like an agent, the whole of the system. Because we have a management environment that will analyze, we plan some action here in the planning, etc. So we have this this autonomic loop. So this can be like an agent, but also each node, of course, if we take the agent, interaction agent inside, each node has its own behavior. So in external point of view, it can be considered like an agent. But also the computation flow, which interconnect, which are, of course, the computation flow will connect a set of services. So we can have a complex processing, including artificial neural controller, in which we can compile and code some planning, etc. So this is also can be viewed like an agent. And the way to model the computation flow is, as I previously said, it's like can be viewed like a simple reactive agent. It's just if else. So what I found funny to do that is that all the system is an agent. Each component of the system is an agent. The connection between the agents are the agents, and something is everything agent, but not with the same terminology at the end of agent. So.
Okay. Okay. Just another question related to this aspect, and now it's for the what you call the learning part, the intelligent part of the system. Tell me if I'm right. So in each neural network, you learn a kind of behavior, okay, and then you do the learning previously, okay, offline maybe,
Exactly,
and then you deploy this architecture. So what happens when you have situations that are not really similar to what the system have learned? The capacity of what is the capacity of adaptation of your system? This is the first one. Or how I can imagine that you have done already a lot of work, but I would like to have your insight about these questions. How to deal with adaptation in this case, and the other question is how to deal with abstraction. For example, if you have a new situation which is that you have developed in the project in MIT, for example, by using this deep learning architecture, you were able to learn low-level features and then abstract this. Could we imagine something similar in your system? Because if you learn daily life situations, generally we need abstraction to understand this. How could you imagine?
Very, very hard question in EA, knowledge transfer. It's very hard, and more particularly the neural encoded knowledge transfer. So I will take the first question first. For the adaptation of I have a data slide now. Yeah. So this is here the loop of adaptation, and it's obviously not. Initially, I wanted to design the artificial neural network at this level, and at this level, like we can have a reactive learning. But because I'm on microcontroller, I have to forget that. I'm sad. So I figured out another approach, which to use an ALC services, but the counterpart to be efficient in terms of computation, I cannot have real-time. I take care because there is some real-time people here. Online reaction. Online reaction of during the learning. So we still have this control loop, this adaptation, but it's very more heavy. such as when we detect that the system don't have the good behavior according to human action. This will trigger some kind of agent that I didn't write here because not in space, which will just push all the, in fact, it will broadcast to the service choreography of this controller that you have to record the context. And all of this node will push their relevant information to the supervisor. And this will be pushed continuously. So when the agent is triggered to push information, the actual neural controller is turned off. So he will play, but he's not controlling anything more. And so, periodically, for now it's hard-coded. In fact, is when the supervisor gets enough information, it's 200 sample of input context. We'll build a new classifier in the same way that in TILSAM architecture. To build a new classifier will be deployed, and when it is deployed, you will switch the agents, which will no more push information, but will connect the optional controller to the. So we have this loop, which is heavy because we have to collect everything, but that's the deal with microcontrollers. So maybe when we will have very good hardware, I'm sure we will be able to do something like that. About neural knowledge transfer, we'll take the slide of deep learning, even if it's. So the idea when you, the idea behind in EMA, I was not so much interested in proposing a contribution in machine learning techniques, but I was more interested in designing a new machine able to execute natively neural network. That was initially my purpose, by thinking that there is a very strong community in machine learning, and I know soon that a lot of people will make crazy things, and we can see now with AlphaGo, we win against human, and so, but the question was, okay, a neural network stays a neural network, it's just a synaptic weight. The question is how to define the synaptic weight. That will define the intelligence of the system. So in EMA, we are able to execute that, and I not really focus on the part of encoding information in neural net, just for a simple example, and in case of TILSAM with the sound. About neural knowledge, I read some recent papers. Some people we are able to switch this feature space, and it's very used by Google, for example, because this now until 2003, the machine learning picture processing was very complicated because we didn't have enough database of picture. So convolutional neural network has been designed by Yann Lequin, which is a French, which was in College of France. He gave a good talk about that. He designed that in 1990. And so it's very old, but we wasn't able to design an IA to play on the go because we didn't have enough database. And by the way, we are able to do that thanks to Facebook and social networking, because people start to tag everything. And so instead of paying somebody to do this tag, we just can collect this information and build big database. And in 2003, we have a ImageNet database, which is here, which is 1 million of pictures with 1,000 categories, which has been for the first time, which has been used to train a convolutional neural network, and now we generate this feature space, and now this feature space is used by everybody. So nobody train a new convolutional neural network; it's useless. So this convolutional neural network are encapsulated in more complex architecture. Like for AlphaGo, it's an actor-critic architecture in which we have one convolutional neural network and one restricted Boltzmann machine, one to learn what is the best action to play, and the other which evaluates the form on the game to determine the valuation of the state, if I can win or not. But for AlphaGo, they use the same thing to recognize a car or to play on the go. That's what is funny. So I suppose that neural knowledge will be transfer will be very interesting in next decade, I suppose.
Okay. Just one last question. Thank you
Yeah,
very
of course.
much. Yes, just to let time for the other. I can maybe ask you some other questions later. It's about your. I have understood that your main contribution is this on this architecture and the middleware, and then concerning intelligence, you used tools that exist and that are able to do the work. So could we extend these tools to other things? Could you imagine in your EMA framework having other type of controllers instead of this? No, should it be neural network based? Or could you imagine some?
That was initially EMA, as Mr. Weiss explained. It's all the idea to manage the flexibility in the design of connected objects. And so here, we have an API here on Conti, which allow you to build what you want of services, and you have an interface to easily connect that to any kind of web service. It can be on the cloud or local. So we can imagine to design real cognitive agent this time inside that, and this can be an agent, like we can do in any multi-agent system, which is connected to the system over these web services. So we can imagine here another kind of services, so embedded on the node, but it can be also, we can have a structural architecture, and if we take a network architecture, we can, so this is our node, but of course we have some what we call border edge router, so it's an interface to ensure communication with external network, which will be gateway probably, but we can also have, so this can be located on the gateway, this can be located on the internet, such as it's a networked architecture with an IP abstraction, so we can have any kind of architecture. And we can also have, I don't have the picture, but it's on the thesis, smartphone. The smartphone, which thanks to the Wi-Fi, can host. So about the Web 4.0, I was thinking, my feeling is that on our tablet we will have intelligence agents embedded. And my question is how to provide to these agents the more flexible way to communicate with ambient system. So by doing that, that's why I choose web services, because I assume that it's easy. But so we can have an agent on the node, on the gateway, if it's an intelligent avatar, numerical avatar, or this can be a remote cloud. I think we can have a combination, of course.
Okay. Thank you again, and congratulations for this presentation and for your work.
Thank you very much.
Merci beaucoup. Grâce à cet échange avec Madame Assas, nous en savons désormais beaucoup plus sur Emma, qu'on peut se représenter en chair et en os. Question intermédiaire, te souviens-tu du destin qu'a imaginé Flaubert à son héroïne Emma Bovary? On va réfléchir. Emma. Je devrais y réfléchir. Bon, je reviendrai. Alors, on va pouvoir maintenant échanger avec les examinateurs, qui sont typiquement des personnes qui t'ont connu au long de ton travail. Je voudrais commencer par donner la parole à Laurent Georges, qui est professeur à l'ESSI à Paris, et qui est probablement celui qui a fréquenté ton travail de recherche en premier lieu. Alors c'est à toi, Laurent.
Merci. Sinon, oui, je confirme, j'ai connu Emma tout petit. Effectivement, donc à l'occasion d'un projet à l'ECE, c'est là où j'ai...
En AG4.
En AG4,
il y a 7 ans.
Ouais. Et c'est là, à cette occasion, effectivement, que j'ai personnellement assez rapidement vu tes capacités d'attraction et de motivation pour la recherche. Donc, voilà, j'ai un petit peu parlé de ça. À l'époque, j'ose espérer que ça a pu t'influencer un petit peu dans ton choix de carrière, et je m'en félicite parce que franchement, quand je vois le travail réalisé là, en l'espace de ces quelques années, ton niveau déjà, je trouve ton niveau assez exceptionnel quand même au départ, mais voilà, je pense que tu as fait un excellent travail qui est reflété par une thèse vraiment très solide et une présentation très claire, vraiment bravo. C'était très bien. Of course, I have some questions, and regarding my my interest, you can imagine the topic I will talk about.
I'm afraid. I'm not free time.
Of course, yes. I'm of course interested in real time, but I know that it's not
Yeah.
hard real time, of course. But I was wondering whether your network average consensus.
Yep.
Yeah, because you say that it will converge. So if it
That's
will,
a good point.
so if it will converge, when?
When? That's the hard point, and that's why it's in a red box. When? I can do this. I can answer you if I have all elements at the beginning, which include the initial preference of each agent. Not very safe. I don't want to centralize, that's the main idea. Everything should be free distributed, and this distribution implies that I cannot get the information of the preference of each agent. And the second one is because this this parameter epsilon we give us when we will converge, because it's an accurate parameter. Yeah? It's depending of the network topology also. So I cannot know that more than if I'm in switching topology architecture. So if the topology can change, this parameter is changing online, not in real time, online. And so the only way that I found a way here on the decision function will allow me to know that accurate to the encoding and the space between each aggregated utility value, if it's possible or not that we make a mistake in the common decision. That means for example, if I have 1.8 and the other agent 2.1, if we apply, I don't know, a round function, I don't know, according to the decision function, we cannot know if one will be take 8 or 9, or so you have to determine when you have enough significant digit to be sure that the decision operator will give the same result for all agents. So to do that, I have a decision function will allow me to do that, to compute that. And so if it's not the case, we apply a second aggregation step with a lower epsilon value that we fix initially. So initially the value is 1, and if we second iteration of its aggregation iteration, we use 10 power minus 1, then 10 power minus 2, etc. Until to be sure that you have enough significant digit to take the decision.
But it's possible that you never reach the case where you have the epsilon value satisfied.
It cannot happen. It will always converge. You necessarily finish on an equivalence or a preference. So, for example, here, this is basically the first iteration in 20 iteration, but here we can see that some agents is very close to the other preference. So that means if I'm stop here, I'm not sure that all agents will get the same decision. But at the second iteration here, it looks like better, but here it's very close, too close. But at the end, we are sure that it's enough spaced to take the and so this decision function determine if it's enough spaced or not to take the decision. And if it's not, we apply again, and at the end we say it's equivalent. We consider that it's equal or not.
But is it possible to bound the number of iterations?
If you bound, you cannot be sure to be enough accurate. So that's the deal. So I know that this will converge, I don't know when.
What is the robustness of EMA to message omissions? Is it possible?
That depends on the application. So it's not about EMA, just EMA is the framework, the mechanism framework. It's more about the intelligent part. For this one is bad. So if we lost the packet, you need to design a service choreography which ensures redundant information to control something. But it can be easily designed. I mean, you can just have a ping, a simple agent will send a request, and that's different way to encode the information. For example, an alarm system, I can have an alarm will send me an information when an intruder is detected, or I can have an alarm which don't give me information when an intruder is detected. So if everything is okay, I say it's okay. When something is wrong, I say nothing. So if we have a failure, we know that there is something wrong, even if it's not the good information, but I know that there is a problem. So this can be a strategy to deal with classical service choreography when the model is not fault tolerant, which is the case of the action error controller. However, for this algorithm, it's fully tolerant. You can lose some packet. You cannot lose too much packet because each time you lost, this will take more time. Because one of these agents will, for example, here we have a perfect example. This one, I suppose that this one here and this one are some agents we lost some packet. So that's why they stop to converge. But when they get back new packet, they converge again. So that's depends. If we are able to design an application fault tolerant, it's okay. Else we have to think better way. I think it's very dependent of the application.
You find a way to characterize the quality of your training according to the time you spent learning?
How many time I need to try?
If would it be possible to have a correspondence between the time spent to learn and the quality?
It's a really. I assume that we cannot know. I mean, we don't know how many times you need to learn English. For me, I need 10 years. For other people, it's 4 years. That depends. So, for a machine, it's the same thing because it's depending of different things. Firstly, is the complexity of the information that you want to encode. Firstly, which will impact the topology of the neural network able to learn that.
But it's not something that you can evaluate?
No, initially you cannot evaluate that, and that's why in each proposal you have a training loop. For example, in TIDSAM, in EMA, I don't know if I have a picture here, but for EMA, for example, you have this loop here for cross-validation. So that's not because you learn that your learning is good. Because what is interesting in learning is to extract a generalization and not to be specialized on such data. So you have to apply what we call a cross-validation. That means that you split your training data set to have data that the system didn't learn in order to evaluate if it's good on that. So initially you cannot know if the learning is good or not, and either you cannot know how many time you need, and because if you have to train again, you need a lot of time. But now in deep learning architecture, such as we can use something like knowledge transfer or similar, you have some components which are already trained. So we know their execution time. So because neural network is real time, that is because when we compute in a neural network, we know exactly how many operations will be operated, so we can know exactly how many time you need. So in deep learning, you can have in very complex architecture some research on that, but in such architecture, it's too simple for. I mean, we have in EMA we have 2 layers maximum. In deep learning, AlphaGo is 64 layer of 10,000 nodes, neurons, so it's very deep network.
Years, tu peux mettre un S même à la fin.
Ah, sorry.
Pour gagner un peu de temps dans ton apprentissage de l'anglais. C'est dommage que tu sois trop jeune pour ne pas avoir connu le fameux sketch de Fernand Reynaud, tu sais, où on demande à une jeune recrue militaire combien de temps met le fût du canon pour... tu as pas connu ça. C'est un certain temps, et c'est la résumé de l'échange qui doit avoir lieu, mais on comprend très bien. Hein, tout ça, c'est... Il y a tellement de paramètres. Alors...
Sauf si méta apprend.
Eh oui.
Sauf si.
Méta le.
Oui, mais ça...
Mais bon.
Ouais,
je peux apprendre
Ah oui, par méta-apprentissage, oui, ça.
Merci beaucoup. Ouais, t'as encore une question.
One last question.
Maintenant, tu connais la réponse.
Just one clarification. You say that because you're event-driven, then it's good because you're not using too much energy just to keep listening to nothing. But how can you detect the reception of message? You have you must provide a certain level of consciousness.
That is the purpose of the MAC layer in the network cyclopan. So this is a part of Contiki. So this is not really in my thesis because my abstraction is to have a microkernel which manages the cyclopan stack for me, and I assume that people will figure out how to do that. However, for example, in Contiki Mac, the node, when he sleep and wake up, he sleep 99% of his time. You can select the frequency. The system, it's like a mailbox. So when a node has to transfer a message to another one, when the other one is wake up, is synchronized, and he will receive you have a message, and he will stay wake up more time to get this message. So it's very slow too, because if you just have that depends on the application. If you want to make streaming, it will not work. But if you just want to send to carry the information that the temperature value is that, it's very efficient, and even more, you can schedule the packet transmission over the network during the not sleeping. But there are a lot of different strategies. I think, if I'm not wrong, in Contiki you have 9 different MAC layers that you can switch. And by the same way, you have a lot of different routing strategy. By default, you have 3. I always choose the ones advised by the IETF, such as it's a normalization institute for that. So, but
Okay.
Merci beaucoup Clément, merci beaucoup Laurent. Alors, on a compris, tu as fait un travail transdisciplinaire, extrêmement riche, et il était également nomade, et ça t'a amené à terminer ce travail au prestigieux Massachusetts Institute of Technology, dont nous avons la chance d'avoir avec nous un des directeurs, et en tout cas le patron de l'équipe qui t'a accueilli, M. Joseph Paradiso. Donc vous allez pouvoir poser des questions if you want. If you have any.
Of course. Thank you for all of the great work and a very good presentation, Clément. You synthesize a lot of different topics and different techniques together, and it's an impressive piece of work to be bringing together. I had one of a student, actually, AI student in my group for many years. He finally did his PhD, but he was working with Minsky and Persinge and others before he came to me, and he wanted to work on sensor nets, and he wanted to make a distributed AI system. He was looking at reflective AI at that point, multi-level stuff, but for sensor networks. And I thought, this is great. A unified system that can run on the nodes as well as on larger, back-end systems, and have it unified, have it be part of the same system, same framework, is a wonderful thing. And I kind of envisioned it as little insect brains in the nodes, and then you've got bigger brains on the bigger nodes, and you're kind of beginning to approach that. But of course, the devil is a bit in the detail, because I build, some of us here at the table build a lot of low-end, low-power nodes in the field. And when you do that, you're really conscious of every little bit of energy that you expend. You write the code specifically to bring that down as low as possible. You look at our Tidmarsh nodes, they communicate once every 20 seconds, and then the battery lasts 2 years. And that's already short compared to how long we want to run the thing. So, for us, power and energy, and it's been said here before at the table, are really going to be paramount in any kind of a framework that's going to run on a low-power wireless node. So I'm wondering kind of how far we can push this. How well does this work to energy-constrained nodes? Do you actually take into account to throttle communications? So as you go down to lower power nodes in your framework in your system, when they're trying to achieve consensus and communicating, do you actually are able to restrict the information the little nodes will send, as you go down this pipeline, and try to optimize with respect to energy consumption in the system?
Firstly, that's why I focus on ambient intelligences and not on wireless sensor network, because in Tilmarch you are very everything is optimized to not consume energy.
Yes,
And
but
so
any wireless network now, that's if it's going to be
exactly.
live on batteries for a long time.
Exactly.
Yeah.
In my case, I'm more interested about wireless mesh network than loosey mesh network, because I assume that this will be in our environment, in indoor. It's not outdoor like in Tilmarch, and so in indoor we have power. My main constraint is I don't want to add more energy cost, a huge energy cost, because if each object is using Wi-Fi, it's just impossible. Wi-Fi, it's 800 milliwatt. 6-low-pan technology is something like 50 milliwatt, so it's 10 less. So that's why I use wired sensor network technology, but I always I was interested more in ambient intelligence system than wired sensor network. Even if what I started with David 7 years ago, we worked with very code to optimize energy efficiency, and that's where I get this knowledge about Mach layer and all of that. That's where I need to wait. But I was really interested about artificial intelligence very soon after that, and so I focus in EA, and after that I say, oh, that was nice also the wired sensor network, and I have to figure out how to mix that. Like everything that I discover, I think each time that I speak with somebody, I think, oh, how can I use that? That was Emma. But for energy, if we really want to consume less, said Emma is event driven. So the node itself is like if we want, for example, in Tilmarch to use something like that, even if it will consume more than what Brian did, because Brian.
Well, it's a simple tree in Tilmarch too. It's not a mesh.
And here, in this case, all of that is event driven. So if you don't have any agents here, you don't have a loop, execution loop. So the system don't do anything.
Of course, just to figure the feature that's triggering your event, you still have to run a process. So it's not for free unless it's a switch or some accelerometer causes an interrupt. If you have to do some calculation, you have to extract a feature on which you can say there's an event.
This is done here in the service on Contiki West Park.
Okay, so you don't consider that to be one of your processes.
Yes.
So you're not turned on until Contiki says there's an event. And you're trusting Contiki is low enough power that you don't worry about it.
Yep. And that's why we have this abstraction. In fact, this abstraction is an abstraction between the electronic engineer people from the software designer. And so here we have, for an electronic people, the loop, internal loop execution will be inside the services. So for an accelerometer, that the designer of the node will determine, oh, what is my energy, what is the energy harvesting that I can have, what is the consumption, what is the need of my object, and so we will fix all of these parameters in the services. So for Emma don't really care because it's event driven about energy, but each node, each manufacturer of the node, of course, have to manage that. In addition of the internal loop of Contiki, because they still have an internal loop to manage radio, but that, I said a lot of people are working on that, and that was my support.
Now, is your neural controller or your neural classifier, whatever, is it built across nodes? So the neurons are shared among different nodes, or is this separate neural net in each node?
Yeah, that was the initial idea. So in fact, we can do that. We can build distributed option neural controller.
It's intriguing. Yeah.
But it's not very efficient if you have more
it would be
than.
you'd have to train to minimize communication between nodes.
Exactly. So, but sometimes it can be interesting, such as we can have here a behavior for a system, and you can have another node like that which is connected, and so you can plug different neural behavior. And so for knowledge transfer also, you can have, for example, a behavior able to plan action. When you need, before that, a neural behavior able to understand the context to say, oh, then we need power, or it's not safe because there is a fire. So you can have a neural controller. We will diffuse this event, and this event will be connected to another neural classifier to take an action. So you can do such kind of architecture which is distributed. But yeah, I think deploying a full neural behavior, it's not working. I mean, I cannot run more than 3 neurons, so it's like a ant.
Well, I mean, the little nodes are definitely going to be like ants compared to the rats and mice and monkeys and further and further out. With the Tidmarsh, we would build this array of 30 microphones. And what other kinds of things would you like to run on it? I mean, you run your classifier, and you know we have some bugs to work out, but it's a great start. So it begins to work. But what other things would we want to do with 30 microphones? It would be interesting.
More than firstly, we will do the second part of geolocalization.
Yeah,
I think that's the first things to do.
Yeah.
But what can be interesting if I'm able to do the stochastic learning that I propose to discuss here, which can be used for bird song classification, we can also use to predict event diffusion in reality. And an idea can be also to put that on the sensor data, and that I plan to use a long short-term memory neural network, which is used by Google Translation, which allows us to predict next state of a successive event diffusion. And so if we plug that on Tidmarsh, something which can be interesting, I don't know if we can, but to say, oh, probably this thing will happen in reality, and in the reality, to have a camera moving and to focus, and we wait. Oh, that's happened or no, and so it's like
because you hear a sound and then you associate an activity or a phenomenon with the sound, so
and
you focus your resources on that because you know what to expect.
Yep, that can be an idea, but also in more about temperature or of that. For example, if you have some sense of wind and temperature, and of that, have a prediction that in this area of Tidmarsh that the temperature should fall very soon, and so to anticipate it. This can be in short-term anticipation, and I think this can be interesting.
Speaking of this, one last question. In TIDS-M, you used, of course, a neural net, and you only used some 500 milliseconds of audio, which for birds can be difficult because their calls can vary and have preambles, and different parts of the bird call, there's more ambiguity. And in addition, they have different calls. So they'll change their call if they're under threat or if they see another of the opposite gender and stuff like that. They modulate and change them a little bit. People, I think, so far have been extracting features using HMMs like the old days of speech recognition to try to look at the sequences of things. Would you, going forward, would you do anything like that? We certainly, I think you have to increase your buffer, and then we can say more about the calls being more robust. But would you go to a state-driven model that has a defined sequence, like an HMM as opposed to deep learning? Do you think deep learning could do the whole thing?
A kind of architecture can do that. It's a long short-term memory that was the plan. Because 500 milliseconds is good to cut the start or the end of a word. The same thing for a bird. And the interest of long short-term memory, it's a recurrent neural network in which we will try to predict the next state and the next state and the next state. Like when we try to translate on Google, it will make some correction because it will predict the probability the next word is this word. So you don't understand what it translates, but you know that probably after this sentence that should be, and we have this same mechanism in our mind when we are able to anticipate the question of somebody or the answer. So I think that LSTM can be very helpful instead of increasing buffer, because the problem to increasing buffer is that we explore the dimensionality issue. For 500 milliseconds at 1 kilohertz to 8 kilohertz, it's generating a vector of 80,000 dimension. So 80,000 dimension without deep learning, it's impossible. I think in traditional machine learning, people build a self-funded feature of 40. So with traditional approach is 40. Now we can manage 80,000, but just adding more millisecond, like 1 second, it's 160,000.
But the bird call, it's so critical because
Yeah.
you know,
So
you recognize typically.
that's why the strategy of FLSTM, if I'm able to anticipate that the next sound of in the sound and give
It's a bit like the old HMM work. It's the same kind of hypothesis. But, and then getting rid of noise with wind and rain.
This should be the same.
You want to be able to separate those features out or separate that domain out.
Yeah. I expect that this will solve all of our problems.
Good. We look forward to it. Thank you.
Merci beaucoup. Merci beaucoup, Joseph. Merci à toi, Clément. Alors, ce qu'on peut faire maintenant, si vous voulez bien, c'est avant d'entendre le directeur de la thèse, on pourrait entendre nos chercheurs invités, qui sont des industriels, et qui ont fréquenté Clément dans son travail aux confins justement de l'opérationnalisation. Alors je donne la parole à monsieur Jean-Marc Lacroix, qui est chercheur à Thales Security. N'est-ce pas?
Eh bien, merci de m'avoir invité tout d'abord. Puis je mesure le chemin parcouru lorsque nous étions il y a quelques années avec Laurent à l'SCE en train de travailler sur des cartes au fin fond du code de ComplikyOS et quelques patchs, si tu veux, qui n'apparaissent plus du tout. Donc, ce monde a été gommé, n'est-ce pas? Le monde du hardware a été gommé, le monde du software bas niveau a été gommé, et tu commences déjà à parler par une abstraction qui se situe déjà à peu près au niveau 7 du modèle OSI. Donc j'ai quelques frustrations, étant donné que mon monde et à moi est plutôt dans celui qui est plutôt en bas, n'est-ce pas? Et je constate une fois de plus que tu as su t'en sortir avec brio et mélanger toutes ces technologies et toujours aller de l'avant pour essayer de les faire communiquer. Et ça, c'est quelque chose qui t'honore parce que Dieu sait que certains de mes collègues sont là aujourd'hui. Nous qui avons mené dans le guidon, dans les technologies entre les couches 1 à 4, on a parfois bien du mal déjà à les faire fonctionner et à essayer d'apporter de l'innovation là-dedans. Et toi, tu as été capable d'aller au-delà. Donc franchement, mes félicitations à ça pour toi. Alors évidemment, il faut que je trouve une question, et je pense que la question, tu l'as trouvée, vu mon activité. So, just only one question is of course about the security aspect. not for...
I have one slide for you.
I would like to thank you very much, but of course not military the telecommunication aspect, but what do you think about the capabilities to introduce more secure VPN or other thing into your systems? This is my only question.
It's a very huge question because in a literature reviews there are a lot of ways to secure the system. I propose an hybrid one. So basically we can think to secure our node communication like secure at level 2, so at MAC layer to provide peer-to-peer encrypted communication. So each node will get a secure IP which will be used to ensure communication with the neighbor. And so it will encrypt the packet, encrypt again for the next neighbor, etc. So it's very efficient in terms of security, but it's horrible in terms of efficiency because we still on a microcontroller. Even if you have now a AES dedicated chip to do the task, it's still heavy to do that. So other people try to propose security like IPsec. We can do that, but same problem. But when you do IPsec, the problem if a hacker is able to get your secret path, your AES key, or your wired sensor network is corrupted, he can do what he wants. So other people are thinking about layer 7. With the COPES that we did with our students, which ensures that at least distributed applications are encapsulated into namespace. But if you corrupt that, you are not able to, you can corrupt the integrity of the application. So basically you can do at second layer, 3, or 7. What I propose here, because I'm in so this is good, you can use for example a 7 or this kind of, when you hardcode in your node the IES key, or at least you have a way to deploy it with the RFID or what you want. The problem is what to do when you have to dynamically reprogram your system. Because that's the challenge of EMA. You can dynamically reprogram the service choreography between the choreographies. So you have to be able to deploy also the IES key. And so if you use still the same, and if you have, for example, several service provider, EDF, Thales Security, I'm not sure that you will be agree to share your AES key. So we have to find a way.
Why not? I don't know.
So I try to split everything. You have two types of key in EMA. The root key, which is yours. You are the user of the owner of this building. You have a root key. We give you access. So you have the root key of each object. So that means that each object has an AES root key hard-coded, or that you can have an upgrade way to do that, which allow you from the supervisor to manage each node independently. So that means if somebody gets the root key 0, he cannot corrupt other node. But now how to manage distributed communication between this node, because he cannot use this root key. So we will build service choreography, and each service choreography will have its own AES key. So in fact, when I talked about resources, each resources has a table of AES key, which define, which will be used to unencrypt the communication corresponding of the service choreography use. So for example, this node to communicate with itself, we use this key to encrypt this communication, and will be used and will be encrypted thanks to this key stored on the same node. And so when this node will communicate with this one, he has this AES key, which will be used by this one to unencrypt the communication, and this AES key allow you only to modify these resources. So if somebody gets it, he just can modify these resources. He cannot modify other resources on other node, only on this node. Only one resources, so okay, if I have a temperature value, he can change it, but that's all. So how to deploy that? In fact, when we build the compose agents, each payload is also encrypted in IES. So I mean that the last deployment agent is encrypted and encapsulated in another one which is also encrypted. So we have some problem with IES that you know have encryption of encryption, and we have some issue about that. But you deploy the key at this time. So when the node arrives, the agents contain the key associated to the resource to install. So at the same time you deploy the application, you deploy the key, which are encrypted by the agent of deployment, itself encrypted. So everything is encrypted during the deployment process, and you launch the agents using a root key of any of the object according to your mapping resolution.
Thank you very much. And congratulations again.
Merci beaucoup Jean-Marc. Monsieur David Manga est chercheur à l'électricité de France, et il a également fréquenté ce travail de recherche en la personne de Clément.
Alors,
Plus que fréquenté.
Plus que fréquenté, oui, tout à fait. Je pense que j'ai été parmi les premiers à voir les prémices d'EMA. Hein. Et en tout cas, bravo. Hein. Je n'ai que ce mot à l'esprit parce que c'est un travail considérable. Pour moi, je ne sais pas, il y a un bouquin qui vient de sortir de Dominique Guinard et Vlad Trifa on Web of Things, et c'est le Web of Things. Enfin, tu as redéfini, en fait, je veux dire, c'est un bouquin que tu devrais faire, parce que là, franchement, il y a une matière énorme, et tu balayes, en fait, tout le scope de l'Internet des objets, et toute sa richesse. Hein. Et donc, bon, bah, bravo. Et je remarque que j'ai bien travaillé parce que je vois le mot énergie partout. Dans tout que ce soit au niveau le plus bas, hein, où tu essaies de récupérer l'énergie au niveau du Mac, hein, tu dors beaucoup. Hein, narcolepsie, hein, les narcoleptiques, hein, ils sont chez toi, ça existe. Et au niveau le plus haut, puisque tu négocies l'énergie, je vois, tu as dit à un moment donné que tu négocies entre un producteur et des consommateurs. Hein, donc tu te places dans le cas de justement l'autoconsommation. hein, là où les gens disposent deviennent des prosumers, hein, donc ont la possibilité. Donc l'énergie est à tous les niveaux de ta réflexion. Hein, et donc, bah, je veux dire...
On n'a pas parlé d'énergie à la demande.
Oui, il te manque l'énergie à la demande. Voilà, c'est le next step. Alors, let's switch to questions I have in mind. When I read your thesis, I saw that you have used the very constrained hardware. It's 8 bits, you know, 10K. It was a time when we met.
Yeah.
6 years ago.
Yeah.
Right now, it's in 22 bits, 32 K, and at the same price.
Yeah.
I know that you look at the price. You wanted everything to be cheap, but okay, what will be IMAC 2 with this new hardware? What will you change to your ideas?
Why I say to use such a very constrained embedded system is because when you can do less, you can do better. And
What
because
can you do
if I start to use, for example, a 30-bit system with 200,000 kilobytes of RAM memory and what we can find on the market, I will not be interested in the execution efficiency, and I will do like everybody. I have space, I have computation, so I can do my application with this power. But me, I was more interested in designing a framework. To do the framework, I need a constraint, like to write my thesis. To write my thesis, I was thinking, okay, you have to write this in 10 lines. Why? It's stupid to do that. But this is the same way. I need to have constraints to fill this constraint. And now that Emma is working on 8 kilobytes just to turn on and off a light, now we can start to think how to use that on more powerful architecture for very interesting applications. That's why if I want to do that now, I mean the next step for me with Emma is to build a real Emma, so to fix a good hardware, to find a good use case, and to do a showroom. Okay. And to do that, I will use what I need to do that. That's the idea. But for software design, I prefer to use on tiny platforms, such as if it's working now, it will be very easy in large platforms.
And the second question I have in mind, because we always talk about machine learning, and you mentioned offline machine learning. But when you talk about autonomic, I remember the master, you know, Armut Schmeck, these guys, they talked to me about how to change model at runtime. So do you consider changing, for example, learning, incremental learning, you know, learning at runtime? Adding the word runtime to your reflection, to your thoughts?
In fact, you can do incremental learning, like reinforcement learning or such kind of... in fact, it's not... why I didn't work on that in this case is because you can do it directly with a simple agents model. Incremental learning, it's you have a evaluation function to evaluate the value of the next state, and a reinforcement signal to do that. And the reinforcement signal, it's a simple function that you can implement directly on a node. So if you want to train, for example, a neural controller with an incremental approach, you will use an agent to generate this function and to provide you the value. So you can do that, but yeah, you can easily by the same way you can in fact implement AlphaGo on that. It will not work to win against human, but you can do the architecture. You have two ANC here, one for the evaluation, for example, in reinforcement learning, with one, and another one to compute the policy. So you will have an agent which will build this reinforcement signal, and your policy will take the action, and according to external operation on this action by human or else, you will get an error signal, which will be used by the agents to build the reinforcement signal, which will be used to train the neural network. But to do online, as you said, actually the ANC is not able to operate the learning process, so that's why it's offline, because I'm using 8-byte. But of course, that was the deal. I was thinking, okay, you can implement that into a services, but I mean there is so many different ways to train a neural network, and a very so large community of experts, very better than me. So I'm thinking, okay, I will let them do their framework, and when I will want to use their job, I will just download their framework, build the neural network, but I should be able to run it on my system. So I mainly focus on that, but indeed if we want to make on a living, artificial living system, because I think that's the idea behind, we need this to implement an internal learning procedure into the node. But it will not be very difficult, it's in C. It's not the most easier language, but I like it. It's a C, but you have every unit, you have two API, one for the system, one for the web services. So you just have to write it. So I suppose, but that was the idea. Maybe on GitHub I should explain more what can be done. But that's the idea of this encapsulated services, is to allow anybody. For example, we was talking about cognitive agents. We can also implement a services like cognitive agents, a complex planning mechanism. We can think a BDI architecture, what you want. In fact, it should be complex operation should be encapsulated at services and connected by chemistry level. That's the idea of cellular. In fact, a cellular can be complex or simple. In my case, I provide 4 with the ANC, but you can add any kind of cellular that you want, which communicate. It should be connected to other things.
To end, I have a comment. Thank you for the Kid March example, because you know, if you replace the birds, the song of birds, by the songs of the noise of appliances, electric appliances, washing machine, it's the same. If you get rid of the noise, as you mentioned, people that speak, we have the same use case. And second, if you change appliances directly, you change sound by electric log curve, the same, it's a signal. So it's always signal.
You still can train and learn.
Thank you.
Thank you.
Merci beaucoup, David Maga. Je pense qu'il est temps que nous entendions le professeur Cyril Bertel de l'Université du Var, qui a encadré le travail académique de Clément. Bonjour Cyril.
Oui, donc merci. Donc c'est un vrai plaisir d'arriver à cette journée de soutenance de la thèse de Clément, qui vient après effectivement des travaux qui datent d'assez longtemps, d'avant que je connaisse Clément, et puis qui se sont prolongés ces dernières années. Et je tiens surtout à remercier tous les membres du jury. Je pense qu'on a, en discussion d'ailleurs avec Clément, réfléchi à cette composition de ce jury, et je pense que c'est vraiment, je remercie très sincèrement tous les membres du jury. Je pense que ça apporte une qualité supplémentaire à ce travail pour son évaluation et les contributions des rapporteurs qui sont vraiment de grande qualité. Voilà. Donc une thèse, c'est défendre un peu un postulat scientifique, c'est par rapport à des enjeux. Je pense que là on arrive à un résultat qui est quand même tout à fait intéressant. Ce qui est important, ce que beaucoup de gens ont noté, c'est cette approche très, très intégrée que Clément a su gérer sur un problème qui s'appuie sur des choses assez variées, que ce soit sur du hardware, sur des abstractions beaucoup plus élaborées. On parle beaucoup de l'Internet des objets aujourd'hui, on parle beaucoup de systèmes communicants. Je pense malgré tout qu'on arrive rarement à aller à une échelle un peu de représentation de tous ces systèmes communicants vers des choses sur lesquelles on arrive à faire un peu de contrôle un peu pertinent. Voilà, donc Clément a su gérer ça. Moi, je suis intervenu finalement par petites touches sur ce travail. Clément, on peut dire que c'est un système complexe vivant, qui est constitué de nombreux degrés de liberté, comme un système complexe, et puis dans lequel l'idée, c'est qu'on espère pour un travail de thèse, c'est finalement que le doctorant sache justement gérer tous ces degrés, intervenir finalement par petites touches. Et moi, j'ai effectivement, je suis intervenu assez ponctuellement sur ce travail. Donc je voulais quand même revenir un petit peu, comme ça va attendre un peu de mon intervention, sur un peu l'historique de ce travail. Donc c'est vrai que moi je suis intervenu, il y a des gens qui ont pris la parole ici, qui connaissent ce travail, les prémices de ce travail. Moi je suis intervenu un peu après, donc avec une proposition qui m'a été faite donc, par le CE de regarder justement comment ce travail pouvait se contextualiser un peu autour des approches sur les systèmes complexes, ce qui correspond un petit peu aux compétences qui sont identifiées sur le CE, qui est un peu le contrôle des systèmes complexes. Et là, je trouve qu'on a quand même un travail qui est vraiment pertinent dans ce sens-là. Voilà, donc il y a eu un début, les premières fois où j'ai eu l'occasion de rencontrer Clément, donc il y a eu des discussions un petit peu sur les approches très conceptuelles autour de toute cette complexité autour de l'internité des objets. Et puis effectivement, il y a la pertinence de ce travail, c'était tout ce travail d'intégration à la fois sur les couches basses, sur les couches un peu plus abstraites. Et donc il y a eu une phase sur laquelle Clément est à la fois très efficace et aussi apporté des contributions importantes sur la partie architecture. Voilà, qui a conduit, on est sur des approches un peu multiniveaux, donc dans ce travail on a eu aussi ces phases à plusieurs niveaux d'implication. Et puis, après, il y a eu un peu, j'ai eu l'occasion d'intervenir, il y a eu un peu une discussion, un effort pour voir un peu comment on revenait finalement un petit peu à ces approches un petit peu plus conceptuelles sur la systémique, sur cette approche à plusieurs niveaux et comment est-ce qu'on travaille un petit peu sur la fin, la présentation que fait Clément aujourd'hui est vraiment une belle démonstration de la réflexion qu'il a pu avoir ces derniers temps, sur savoir comment on revenait sur... on arrivait à présenter ça sous une approche un peu de l'organic computing et justement de ces aspects sur une approche un peu conceptuelle abstraite. Donc, voilà, je pense que la présentation qui a été faite montre bien tout ce travail de réflexion et c'est vraiment un résultat que je trouve important à la fois pour lui et puis pour la contribution effectivement sur l'Internet des objets. So my English part will be very short because I will not ask for question. I suppose that if I have already asked to Clément, I just profit to this English part to thank a lot Joe Paradiso for the proposal of Clément to come in MIT, and I think it's a very, very nice final part of this PhD.
Our pleasure. Thank you for letting him come.
And I think a lot of PhD students in computer science dream to make such part of PhD. Okay.
Merci Cyril. Merci Cyril.
moi je voudrais dire que je suis très impressionné par ton travail, par sa qualité, par l'incroyable précision de la navigation que tu as fait pendant ces échanges, pendant cette question. Il a été précisé que oui, pour aborder cette question complexe, tu savais t'y prendre. Je me demande si ce n'est pas ce cocktail de flegme, en même temps d'autorité, de finalisation, d'intensité dans tes projets, qui est sans concession tout en étant patient. Enfin, je trouve que, je me demande si tu n'as pas inventé une méthode, en plus d'avoir réinventé l'Internet des objets, au sens où Bakounine disait fort joliment que si Dieu n'existait pas, il faudrait le réinventer. Hein. Je ne dis pas que tu l'as réinventé autrement. Tu as vraiment, tu nous as relu la totalité de ce mouvement-là. Et je me demande, oui, si tu ne proposes pas une méthode faite de cette pluridisciplinarité, de cette patience dans ton enquête. Et du coup, finalement, j'aurais une question un peu personnelle, même s'il y a encore des gens pour longtemps, mais je voudrais savoir ce que tu as envie de faire maintenant, toi qui as traversé l'académie française, sans mauvais jeu de mots, l'académie en France en tout cas, l'université, qui est un cas de figure assez étrange dans le monde, mais tu as aussi vu d'autres endroits, comme et pas les moindres, comme le MIT, et tu as côtoyé des industriels dans des grands groupes. Qu'aimerais-tu faire maintenant? C'est un peu discret, hein, as-tu déjà des idées sur ce qui te plairait de développer par la suite?
La question qui sèche. Ce que je sais, c'est que j'adore apprendre. Et que, comme disait Jourdan, enseigner, c'est apprendre 2 fois.
Écoute, regarde, tu vas voir. Chapitre 6, c'est exactement ce que je
La citation. C'est peut-être pour ça que
tu lis en plus, tu lis dans les...
Ah oui, tout à fait. Donc oui, enseigner, c'est apprendre 2 fois. Donc ce qui est sûr, c'est que j'ai énormément appris des étudiants que j'ai eu la chance d'avoir en cours. Ça, je tiens à le dire, il y en a certains qui sont ici, qui sont devenus amis, fortiori des choses. Donc j'ai appris beaucoup et je leur dois beaucoup pour ça. Et donc sur l'après, en fait, ce que... Bien sûr, Emma, j'ai envie de la continuer, et puis c'est un espèce de melting pot intellectuel pour moi, où je m'intéresse à de nouveaux sujets. Enfin, à un moment, j'irai un peu rapidement du temps réel, des choses pour voir comment ça pouvait se greffer, etc. Enfin, c'est toujours ça, donc c'est sûr que je veux continuer là-dedans. Donc ce qui est sûr, c'est que je veux aussi, c'est que M. Paradiso m'a proposé de retourner au MIT pendant 9 mois, que je vais accepter avec grand plaisir, parce qu'il y a beaucoup de choses à apprendre. Énormément de choses, j'ai appris beaucoup de choses sur prendre de la hauteur justement, prendre confiance en ses travaux, et je pense que sans cette expérience, je n'aurais pas présenté mes travaux tels que je les ai présentés aujourd'hui. Et donc voilà, donc y retourner, et puis après ben, c'est sûr que là, moi je me vois dans une carrière de chercheur, d'encadrement dans la recherche, donc mon envie c'est de plus rapidement de pouvoir m'imprégner de ça, de pouvoir aider de jeunes thésards ou masters qui sont intéressés dans ce genre de sujet, qui sont le deep learning, l'intelligence artificielle et le monde de l'IoT. Et puis voilà, de poursuivre dans cette voie, tout en ayant une dimension concrète, c'est-à-dire que je veux aussi m'intéresser à la manufacture. J'ai eu l'occasion de découvrir au Media Lab, où là-bas, quelque chose qui n'est pas fabriqué n'existe pas. Donc il faut savoir quand on commence, il ne faut pas commencer par le logiciel, on commence par le matériel. Parce que s'il n'y a pas le matériel, il n'y a pas de logiciel. Donc c'est des choses où, voilà, où j'aimerais faire fabriquer un tas d'objets, donc travailler dans du Fab Lab, faire des objets, faire de la recherche à la fois concrète, théorique, en prenant de la hauteur, des fois se poser des questions philosophiques, mais toujours dans de l'échange et toujours pour donner, partager et enseigner, parce que c'est comme ça, je crois, qu'on apprend.
Merci beaucoup Clément. Donc tu reliras Madame Bovary dans ton vol Paris-Boston. Merci beaucoup. Je propose que nous allions délibérer à l'extérieur, ce qui permet, ce qui nous permet, oui, non, on a une salle, hein. Ce qui nous permet de rester ici en nous attendant. Merci Clément, à tout à l'heure.
Merci à vous.
I remember it is yes.